I will talk about Mikusinski's operational calculus, which I need to spend some time introducing because it may not be familiar to many of the audience. It's a specialized topic that involves both not necessarily involving fractional calculus, but I'm applying it to fractional calculus. So it involves both algebra and analysis. So I believe this audience is mostly from analysis. My introduction is going to introduce fractional calculus and abstract algebra. In order to understand the main topics of the talk, I will introduce Mikusinski's operational calculus, the way it has been applied to classical ODEs, so ODEs of integer order, and to fractional ODEs of both Riemann-Liouville and Caputo type. Then section 3 is my new results on using this method to solve systems of fractional differential equations. So I'll give a brief overview of some other methods that have been used to solve such systems, and then I will talk about how we can solve them using this method of Mikusinski. And in conclusions, I will give some pointers towards future directions and summarize what's been done so far. So let's start by introducing fractional calculus. Perhaps everyone is already familiar, but I'm going to briefly mention what this field is all about. Of course, in basic calculus, we have repeated derivatives and repeated integrals. So derivatives can be to any natural number order. If we want to consider negative integer orders, by the fundamental theorem of calculus, we can sort of interpret an integral as a derivative to negative order. Now, fractional calculus is the study of extending the order of differentiation or integration beyond the integers to rational numbers, hence the word fractional, but also real numbers and complex numbers in the same way. So the most important reference text book in this field is the book of Samko Kilbes-Marichev, first published in Russian in 1987, translated to English by 1993. I've also mentioned here a few other important textbooks in the field that I can recommend. The first ever textbook specializing in fractional calculus was Oldham and Spanier in 1974. And then we have several others from the 90s and 2000s continuing up to today. So here are the basic operators of fractional calculus. What are we studying in this field? We have fractional integrals, which are defined by the first formula here. So this is the integral to order mu. Mu can be a real number, a positive real number, or a complex number with positive real part. This positive real part requirement is necessary for the integral to converge. A is a constant of integration. T is the independent variable, and RL is short for Riemann-Liouville. There are many different types of fractional integrals, so we need to say this RL to be clear which type of integral we are using. The constant A is often taken to be 0 or minus infinity, and there is a transmutation argument that shows that taking any finite constant A is essentially equivalent to taking A equals 0, which makes sense because it's like a starting value, an initial point. You can always set the initial value to be 0. Now, we have fractional derivatives, two different fractional derivatives associated with the same fractional integral operator. So there are the Riemann-Liouville derivative and the Caputo derivative. The Riemann-Liouville derivative is defined by an ordinary derivative of a fractional integral. The Caputo derivative is defined by a fractional integral of an ordinary derivative. Now, n here is chosen in a particular way, which I will show on the next slide, but essentially we need n to be a natural number and n minus mu to have positive real part to make sure this really is a fractional integral according to this definition and an ordinary repeated derivative in the classical style. The advantage of the Riemann-Liouville derivative is that if we consider the analytic continuation as a function of mu now being a complex variable, mu is on the right half plane for this first definition. If we want to extend from the right half plane to the left half plane, there is a unique way to do that, and what it gives is exactly the Riemann-Liouville derivative. So from this viewpoint, thinking about complex analysis, the Riemann-Liouville derivative is the only natural extension of the Riemann-Liouville integral. However, in terms of applications, modeling using differential equations to model things in the real world, Caputo has been found often more useful because of the initial conditions associated with differential equations of Caputo type. So a Riemann-Liouville fractional differential equation would involve would involve fractional initial conditions, whereas a Caputo differential equation would involve sort of standard initial conditions, non-fractional. Sorry, I'm not sure if you can see the bar at the bottom of my screen. I'm just trying to see how to get rid of it. Hide floating meeting controls. Yes, now I think you can see more clearly. Okay, so how to define n in terms of mu? I put a special slide for this because in some ways it's a very simple point, but it is something that has been often misunderstood. And even in some good papers by top researchers in this field, sometimes this point is not quite written correctly. So the problem is there is no single formula that can always define n in terms of mu for any complex mu. So we need this split domain definition. We need to consider two different cases if mu is allowed to be complex and if we want both Riemann-Liouville and Caputo to be covered. So n is taken to be the floor of the real part of mu plus 1, unless mu is an integer, in which case we just take n equals mu. Now, this is the same as just the first formula, except, well, obviously, except when mu is an integer. For Riemann-Liouville, we can actually use that first formula always. For all values of mu, it will give the same result. But for Caputo, we cannot use this always, because if mu is an integer, and you try to use the floor plus 1, in the integer case, that will give you mu plus 1, and you will get a wrong result for the Caputo derivative. Caputo derivative to order mu for integer mu would not be just the derivative, the classical derivative to this integer order. So that's why we need these two different cases. Can we simply say n is the ceiling of the real part of mu? Well, if mu is real, then yes, but we have this tricky case where mu is an integer plus a non-zero imaginary number. So if we consider the definitions, n minus mu, we want to have positive real part. So we need n to be strictly greater than the real part of mu, except in the case that n minus mu is actually equal to 0, because the integral to order 0, well, that's just the identity operator. That is defined. But the integral to a pure imaginary order, for example, the integral to order I, we cannot define using this formula, because we need real part strictly greater than 0. So in the case where mu equals, for example, 2 plus I, we cannot take n equals 2, because that would give minus I here, which is not defined. So we need to take n equals 3, and it will be the integral to the order 1 minus I, which is defined because 1 minus I has positive real part. So it's a tricky point, but I just want to emphasize this sort of a correct way of defining n in terms of mu. Let me also briefly introduce some Mittag-Leffler functions. So we have the original function due to Gösta Mittag-Leffler himself. He published a series of papers in the very early 1900s. Here is his function, E alpha of Z. It's denoted by E because it's essentially like an exponential function. It's like a fractional exponential function. If alpha equals 1, it is a classical exponential function. This, we can say, is equally important for fractional differential equations as the exponential function is for classical differential equations, i.e. very important. It has many natural properties in relation to fractional derivatives. For example, we can see this property here. It is literally an eigenfunction of the Caputo fractional derivative. This function has been extended in many ways. So here we have, I say univariate because this is a function of one variable z. It also has one parameter alpha in the classical definition. Here is the 3-parameter Mittag-Leffler function. It's still univariate. So we have one variable z, but 3 parameters alpha, beta, gamma. This was defined in a short paper of Tilak-Raj-Prabhakar, published in 1971. And this is used to create what's now called Prabhakar fractional calculus. So it's another type of fractional calculus with fractional integral and derivative operators that are different from Riemann-Liouville, containing Riemann-Liouville as a special case. This Prabhakar has a lot of interesting properties, for example, a semigroup property in 2 parameters, beta and gamma, but I don't have time to go into that, so I just give the references. There are also multivariate Mittag-Leffler functions. So bivariate and multivariate. So here is a multivariate formula. There are actually different types of multivariate Mittag-Leffler functions, not only this one, but this one is particularly useful because it has, yes, this one appears naturally in the solution of multi-term fractional differential equations, which is where Rudolf Gorenfloh and Yuri Luchko first discovered this function in the 1990s. They had a series of papers. I mentioned the one where it first appeared, but there were a bunch of others as well. And essentially, the reason why we need this in fractional calculus is, I told you that the Mittag-Leffler function is a fractional version of the exponential function. So if you solve let's say, a simple first-order ODE, you may get a solution involving an exponential function. You solve a second-order ODE, you may get two exponential functions in a linear combination. You solve an nth-order ODE, different exponential functions with a linear combination. But for fractional ODEs, there's only one fractional derivative involved, Mittag-Leffler function. If there's two fractional derivatives, it would not be two Mittag-Leffler functions. It would be a bivariate Mittag-Leffler function, because the structure of the solution space is not so simple. If you have a multi-term fractional differential equation, you need this multivariate Mittag-Leffler function, which is not the same and is not a simple formula from the classical univariate Mittag-Leffler function. So here I mentioned a recent paper of mine where we classified a lot of different bivariate Mittag-Leffler functions. This is essentially n equals 2. And I mentioned this original paper of Gorenfloh and Luchko defining this function. This function has also been generalized further by Emilia Bajlikova and others to introduce an extra parameter which gives a nicer semigroup property. But again, I'm not going into that here. So let me also introduce quickly some basic concepts from abstract algebra. Of course, everyone is familiar with groups, rings, and fields. I want to fix my terminology because the word ring is sometimes defined to require a unity, a multiplicative identity, and sometimes without this requirement. There are just different conventions among algebraists. So the convention that I use is that a ring must have a multiplicative identity, a element 1, essentially. And if it does not have that, I call it a rung. So the word rung is the same as ring without I, and it looks like a sort of wordplay joke, but it is actually a serious mathematical term that is used in the field. So a field, of course, has every element has a multiplicative inverse. So every field is a ring, every ring is a rung. All right. Now, every ring or rung, if it does not have zero divisors, so that means if AB equals 0 always implies either A equals 0 or B equals 0. If you have this condition, then you can extend this ring or rung to a field in a way that's called a field of fractions. So there is a formal construction. The details are not very important. Basically, you think of it as fractions, f over g. So f and g are in the original ring or rung. G cannot be 0, and you sort of divide. And even if you cannot divide in the ring, the dividing makes sense in the field structure, because in a field you can always divide, and you just set it up in such a way that all the operators of arithmetic, adding, multiplying, dividing, subtracting, they work in the way that we are familiar with. So the most standard example of constructing such a field of fractions is going from the ring of integers to the field of rational numbers. We may also go from a ring of polynomials to a field of rational functions. So this is a sort of standard algebraic fact. I mention it here because it's going to be used. It's a very important fact to be used in the construction of Mikusinski's operational calculus. Essentially, we will start off with a ring that is a function space, and we will extend it to a field and solve equations in that field. So here is a summary of the key ideas of this method of Mikusinski's operational calculus. We apply algebraic structures and methods to interpret the operators of calculus. So I'm using this color coding here and throughout the presentation, which can be helpful perhaps in understanding the two-sided nature of this topic. So I use red for algebraic, blue for analytic, and often it is the same mathematical object that we interpret in two different ways. So we start with a function space. So this is a set. Analytically, we think of it as a function space. Algebraically, we think of it as a rung. You see the blue and red. For a rung, we need two operations. We have pointwise addition of functions. We do not have pointwise multiplication. That's not the second operator we use. It is convolution of functions. I will show this in more details with mathematical formulae later on. So this slide is just to summarize what's happening. So this ring we have now, we prove that there are no zero divisors, and then we extend it to a field of fractions. So this field is an algebraic abstraction. So the elements of the field are not necessarily functions. The elements of the ring must be functions because we started with a function space, but the elements of the field are just field elements. They may not be interpreted in any analytic way. So there's only red and not blue in this bullet point. Now, integration, we interpret as multiplication in the ring. Okay, that can be done for ordinary integrals, for fractional integrals. I will show you how. Differentiation is sort of the inverse of integration. So what's the inverse of multiplication? It's division. That's possible in the field, not necessarily in the ring. So we go from the ring to the field, we go from integrals to derivatives. But now let's say you have a differential equation that you want to solve. Your derivative is just a field element. So this differential equation, you interpret it as an algebraic equation. You solve it algebraically in the field. If the solution you find in the field is also in the ring, then because the ring is a function space, you have found a strong solution. Right? So here I've shown the same thing in a bit more visual way. So I've got the same color coding, but also columns on the left and right, analysis on the left, algebra on the right. We start with a function space. We interpret it algebraically as a ring or ring, which we then extend to the field of fractions. The field of fractions has nothing corresponding on the left. It's a purely algebraic abstraction. Integration corresponds to multiplication. Differentiation corresponds to division. So here is the process of solving the differential equation. You transform it to an algebraic equation, solve it in the field. If the solution is in the ring, then we have a solution that is a function. Right? So some brief history of this topic. Of course, Mikusinski himself was the main figure who kind of created this topic. He was a Polish mathematician, graduated from the University of Poznań, PhD in Jagiellonian University, spent most of his career in Katowice, the Polish mountains. So what I've written on this slide, sorry, is not quite accurate. I said invented operational calculus. He didn't invent operational calculus. He invented this type of operational calculus that is named after him. So the concept of operational calculus did exist before him, going back to Heaviside and others, but he invented what we now call Mikusinski's operational calculus. So he lived 1913 to 1987. Yuri Luchko is the main contributor to this field, specifically in the fractional calculus topic. And he is still very active in research, originally from Belarus, but has worked for many years in Berlin. And you will see later on, I will mention many papers of him which apply this method to fractional differential equations. So for ODEs, we have Mikusinski's book, published in 1959. There's a lot of detail in there on how this method works to interpret one-dimensional integer order derivatives, integrals, and to solve ODEs of various types. For PDEs, there is not much in the literature. So there is one paper of Gutterman in 1969, where this method was successfully applied to solve PDEs. This paper has very few citations. Most of the citations it has, I think, are from me. It's sort of gone under the radar because Gutterman, after he finished his PhD on this topic, he didn't continue in research. So he didn't continue, nobody else continued in this direction either, and it just sort of stagnated. There is a very nice survey paper, Rychkov, Prudnikov, Shishov, originally in Russian in 1979, Journal of Soviet Mathematics, in English in 1981. And this covers all the work on this field up to, of course, the time of publication. So there's been a lot since then, 80s, 90s, and onwards, but it's a nice overview of what happened up to that time. Now, something that you may not have noticed yet, because I haven't shown any formulae, but you will notice it in the later slides, is that the expressions we get when we use this method, they look very similar to what you get from Laplace transforms. Laplace transforms also involve taking a differential equation and transforming it to an algebraic equation. But the mathematical justification behind it is different. So in the Laplace transform, you have the t domain and the s domain, and you transform from one domain to the other using some integral. Here, we don't need to have any integral. We don't have different domains. We just consider that our functions are in some algebraic space, and we extend this algebraic space, and we solve everything within a single field. Now, the elements of the field are not all functions, but they're all within this field. And you can set this field to be much bigger than the space of functions that have Laplace transforms. If you want to use Laplace transforms, you need some condition like exponential boundedness, otherwise the integral will diverge. But for this method, you don't need any such condition, so it works in larger function spaces, and that makes it, from a mathematical viewpoint, more powerful. You can deal with functions like e to the power t squared, for example, which don't have a Laplace transform because they're not exponentially bounded. Now, why in that case is Laplace's method so powerful and Mikusinski's method is not? I believe the answer to this is simply that Mikusinski's method needs a more advanced mathematical background. So Laplace's method, the method of Laplace transforms, can be taught in undergraduate courses for engineers. You don't need to know much mathematics to understand it. It's just integration. Whereas for Mikusinski's method, you need a bunch of concepts from abstract algebra, which engineers perhaps never learn, and even applied mathematicians may not learn all of these things. So it hasn't had such an interdisciplinary appeal. There is a nice discussion paper, which I also cited here, of Flegg, which goes into more detail of this comparison between Mikusinski and Laplace from different points of view. So it's not a mathematical research paper. It's more like a mass education discussion, but it's an interesting read. So let me now give you some details about how this method works for classical ODEs. The function space we're going to use is simply the space of continuous functions on the half line. No boundedness assumptions, no differentiability assumptions yet. This space forms a ring under the operations of addition and convolution. There is a theorem of Titchmarsh, which you can find in chapter 2 of Mikusinski's book. Chapter 2 is all about that theorem and its proof. It's quite difficult, which states that this ring has no zero divisors. As we know, any ring with no zero divisors extends to a field of fractions. So here I use a nice notation, which is the convolutional division, because I want to remind you, whenever you see this fraction, that it's not actually a fraction in the ordinary sense. We may divide, for example, a polynomial by a polynomial, and we will not have a rational function. We may not even have a function at all, because it is not pointwise division, it's convolutional division. So that means this f over g is something such that when you take the convolution of that with g, you get f, right? So as a function, f over g does not always exist. You cannot always divide in a convolutional sense. But from the construction of this field, because it's a field, we can always divide. Everything has an inverse. This is always well defined in the field. Now, integration can be very easily interpreted as multiplication, by which I mean convolution, by the constant unit function. So if we let L denote the function that's always equal to 1, then L star g is the integral of g. Because, simply look at the definition, if you put f equals 1 always, then you get the integral of g. Okay, so integration is multiplication, then differentiation should be division. Let us introduce S to be the algebraic inverse of L. So M is the field. Yes, so M is the field of fractions, all right? Elements of the field are not necessarily functions, but we know that this S exists in the field. I, the identity element, is also not a function, but it exists in the field. An identity on the convolution would be something with similar properties to the Dirac delta. So you could interpret this using distribution theory, but here we have a different and algebraic interpretation instead. So S acts as follows. This is basically the key theorem of Mikusinski's theory, and I'll give you the proof because it's a short and elegant proof. Basically, we use the second fundamental theorem of calculus, which says that if you integrate the derivative, the integral of f dash, which we have here, is f of t minus f of 0. So that means f as a function is equal to L star f dash, the integral of f dash, plus f of 0 times L. So f of 0 is a constant. We have a constant function. L is the constant unit function, constant multiple of that. Okay, so this here at the end is a purely algebraic equation. We multiply that in the field by S. S is the inverse of L, so we get S star f as the first term, f dash as the second term, and S star L becomes the identity. So we have this third term, and that gives the result. Okay, so that means if you have a derivative, f dash, you can interpret it in the field as just something involving f, S star f minus f of 0i. So let's say we have a differential equation. Here is a simple linear constant coefficient inhomogeneous nth order differential equation. So we think of this as an identity between functions. The right hand side is h. The last term is A0y. The next term, what is y dash? We know that's sy minus y of 0. I've slightly compressed the notation here. So technically, I should say s star y minus y of 0 I. If it's the identity, then we just suppress the notation. Star, we also suppress the notation because there's only one multiplication in this field. Okay, you can extend the same thing to the second order, third order, nth order derivatives. And if you look at this expression for the nth order derivative, now you understand what I mean about Laplace transforms, right? This looks exactly the same as the formula for the Laplace transform of the nth derivative. But the function y here could be something like e to the power t squared, which does not have a Laplace transform. So s is not a separate variable. We're not shifting from the t domain to the s domain. S is an element of the same field where h and y and all these functions live in that field. So what we have in red is an algebraic equation within the field, which is perfectly valid. And we can rearrange that equation algebraically. So the big fraction in red is a solution, essentially, of the equation. It's y in terms of the known function h, the initial conditions, which should be specified for a well-posed problem, and this s, which is not an unknown thing. It's a field element, but it's fixed. It's a known thing. Now, the problem is, how do we know that this is a function? It's a convolutional quotient. It involves polynomials of s. We know s is not a function. So how can we rewrite this as a function? Well, what is a quotient of polynomials? In basic calculus, a quotient of polynomials, we would say, is a rational function. How do we deal with rational functions? We write them as a sum of partial fractions. So let's turn this into a sum of partial fractions in terms of s. So our basic unit as a partial fraction would be something like this. Identity over s minus constant, right? That's what we see. We may have a constant multiple of that, but that's the basic unit of partial fractions. So we interpret this as a function. Okay, I'll show you all the steps because it's quite fun and not too difficult. Multiply by L on top and bottom. All right, L is a function. It's the inverse of S. So when you multiply S times L, you get the identity. Okay, so we have L star. Now this identity minus something inverse, we interpret as a geometric series. As long as this converges, everything will be fine. Let's write it, and then we'll check the convergence at the end. Okay, so we have L star, the geometric series. What is the convolution of L with itself, n times or n plus 1 times? That turns out to be a polynomial, a power function. So we have t to the n over n factorial, multiplied by this constant p to the power n. What is that series? Simply the series for the exponential function, which we know is locally uniformly convergent, entire function on the whole, everywhere. So the convergence is justified, and this is the functional interpretation of this algebraic element. So if our rational function is a linear combination of things like this, then we end up with exponential functions, a linear combination of exponential functions as the solution. Okay, if we have distinct roots, if we have h equals 0. If we have an inhomogeneous term, h, then it will be slightly more complicated. If we have repeated roots, then it will also be slightly more complicated because this e to the power pt should be multiplied by something. But essentially, this is what we have. Now, this, of course, is a result that's known from classical ODE theory. So you may think, so far, this method has not been useful. It's only given us things we already know from other methods, not even only Laplace transform, like this is known in any basic course on differential equations. So it turns out that Mikusinski's method seems to be not so useful in cases of variable coefficients. I can explain why, but basically it's about the fact that we have this convolution and we cannot easily multiply by something, by another function as pointwise multiplication. So where Mikusinski's method has really been useful is in fractional calculus, because in the fractional case, this method has been used to solve problems that had never been solved before by other methods. So if you have a multi-term fractional ODE, you cannot easily solve it using some of the standard methods from classical ODEs. So you need something more advanced, and one of the things that works is Mikusinski's method. So this basically started with Luchko's work in the 1990s. I mentioned him. I mentioned one of his papers with Gorenflot. Here's a bunch of other papers. So we have Hadid-Luchko. They solved Riemann-Liouville fractional differential equations. Luchko-Gorenflot solved Caputo fractional differential equations. Luchko's single author paper sort of summarizes the work of these other papers. So he talks about Riemann-Liouville, about Caputo, also other operators like Edey-Kober. And his work is also continuing up to the present. So I've also mentioned some of his recent papers, which are extending the same method of operational calculus to the so-called general fractional derivatives, which in this context means fractional derivatives with Sonin kernels of various types. Okay, so first level is a sort of generalization of Hilfer, but also with Sonin kernels. So I also want to mention in the recent years, as well as Luchko's work, I've also began working on this topic in the context of generalized fractional calculus. So my first papers on operational calculus were cited here as 21 and 22. This was for fractional operators with respect to functions, which is quite a natural generalization. It's another sort of generalized fractional calculus. Then I also generalized that even further a couple of years later to Mikusinski's operational calculus for conjugated fractional derivatives using transmutation relations. So Fahad is one of my former PhD students. Also Rani is another former PhD student of mine. We worked on this method for Prabhakar differential equations, fractional differential equations, also together with Zhivarat-Tomovsky, and fractional calculus with general analytic kernels. So there's lots of different types of fractional calculus. In this talk, I'm focusing on Riemann-Liouville and Caputo, but there's many other operators and generalized operators as well. So let me give again an overview of how this theory works in the fractional setting. So the rung here we use, the function space we start with, is different. Instead of the space of continuous functions, we take the space C alpha, which is defined like this. So it is continuous functions on the half line multiplied by a power function. So the most common value we take for alpha is -1. P greater than -1 means that the function is not necessarily continuous at 0. It can have a singularity at 0 if P is negative, but it must be integrable because greater than -1 means you can integrate it around 0. And because it's continuous at all positive values, it would be therefore locally integrable on the whole half line. Okay, so these spaces are nested inside each other. They satisfy a convolution relation, which means that this space again forms a rung under addition and convolution. Again, we can show that this rung has no zero divisors, which means it extends to a field of fractions, which we denote by M subscript alpha. Okay, so the Riemann-Liouville fractional integral can be interpreted as a convolution because if you recall the definition of the integral to order mu, it is this, which is exactly the convolution with this function h mu that is a fractional power function. Now, there is a nice semigroup property that says that Riemann-Liouville fractional integrals form a semigroup, and also these functions h mu form a semigroup under convolution. So when you extend to the field, the semigroup becomes a group, and fractional derivatives of either Riemann-Liouville type or Caputo type, remember there were these two kinds of fractional derivatives both associated to the same fractional integral. So we would expect these to be somehow inverses algebraically of this element h mu. If the integral is multiplying by h mu, the derivative should be multiplying by the inverse of h mu. So s mu denotes the inverse of h mu, and we have the following results. For the Riemann-Liouville derivative, it's S mu star F minus something involving fractional initial values. For the Caputo derivative, it's again S mu star F minus something involving non-fractional initial values. As I mentioned before, this is the key difference between Riemann-Liouville and Caputo. Riemann-Liouville initial values are fractional, Caputo initial values are of classical type. Okay, so these are the interpretations of fractional derivatives in Mikusinski's operational calculus. Now we can solve a fractional differential equation. We start with a simple case, one single fractional derivative. So this derivative of y we interpret as S mu star y minus that term, which I've taken over to the right-hand side. So the right-hand side now is essentially a known function. G1 depends only on G, which is fixed, and the initial values, which should be known for the initial value problem to be well posed. So then you get in red y as the algebraic expression from solving this algebraic equation. And then in blue, we can interpret this. We've got h mu to the power n. So it's a convolution of h mu with itself n times or n plus 1 times. And we end up with this expression, When you put it into the series, this gives a Mittag-Leffler function, and therefore the series is convergent. This geometric series idea is justified, and we have our explicit solution function as a convolution of G1 with this Mittag-Leffler function. Okay, so when you have one single differential operator, one fractional derivative here, you get a univariate Mittag-Leffler function in the solution. If we have a multi-term equation with n different fractional derivative operators of independent orders, you see this mu and mu1 up to mu n. They can be anything. They don't have to be related to each other by any rational factor or integer difference or anything like that. They're totally independent fractional orders. And then the solution involves a multivariate Mittag-Leffler function, because what we're taking to the -1 here is not only two terms, but it's n plus 1 terms, and therefore you cannot just use a geometric series. It becomes more complicated, and that's why we need these bivariate and multivariate Mittag-Leffler functions to solve multi-term differential equations in the fractional setting. So as I mentioned before, the main place where Mikusinski's operational calculus has really been uniquely useful is for fractional differential equations. Recently, again with my former student Nushez Arani, we used this for the first time to solve fractional PDEs. So this is building on the work of Gutterman 1969, combined with the more recent ideas in fractional derivatives. So this is fractional PDEs involving Riemann-Liouville derivatives, and we're also working now on fractional PDEs with Caputo derivatives. You may have heard of the fractional Laplacian, which is also frequently used in fractional PDEs. We could not use Mikusinski's operational calculus for that because of the nature of fractional Laplacian as a global operator. It involves an integral across the entire Rn, or in the one-dimensional case, from -infinity to infinity, and we cannot easily interpret that using a convolution or there's no suitable function space, basically. So I did this short paper with my former master's student, Ibrahim Saleh, and we showed that there is no function space which satisfies the properties that would be needed to apply Mikusinski's operational calculus for the fractional Laplacian. So that's a kind of negative result. Now, recently, there's a couple of papers of Marc Journet, which are analyzing systems of fractional differential equations using Mikusinski's method. So that's the main focus of my recent work here. Let's look at a coupled system of Caputo-type fractional differential equations. I say Caputo type because let's stick with these classical initial conditions that are easy to understand. If I took Riemann-Liouville type equations, it would be more tricky to fix the initial conditions. So let's just stick with this for now. How do we solve this type of coupled system? Well, there are some methods already in the literature. So one way to do it would be to interpret this system as a FDE for a vector valued function. So A here, capital A, would be a matrix consisting of these four constants. Vector X and vector G are with the obvious meanings. You also have vector mu. So this could then be solved using standard methods, the same as what you can find in like the classical textbooks for single term Caputo fractional differential equations. But what's the problem with this? The answer would involve a matrix Mittag-Leffler function. And a matrix Mittag-Leffler function is hard to deal with. You see, there's only very recent work on the computation of the Mittag-Leffler function of a matrix argument. So classical Mittag-Leffler functions, there's classical results. This has been studied quite deeply for a long time, including the asymptotics, the numerics, and so on. There's a lot of studies on this, but matrix-valued Mittag-Leffler functions automatically more difficult, and people are still working on it. So it would be nice if we could get a solution that's not involving matrices, but just functions of a single variable, or maybe more than one variable, but somehow more explicit. So a few years ago, with some colleagues in my department, did I cite the papers on this? Yeah, so there you can see the papers, Nazir Mahmudov and two of his PhD students. We published two papers on systems of differential equations. So again, Caputo, basically similar systems like this, equations 2 and 3. But the orders, the fractional orders, were between 0 and 1. And the solutions were found in a space of continuously differentiable functions, which is really too small a space to be useful for this type of result, because for fractional differential equations, you often need to allow for singularities at the initial value. That's why people use this C alpha space, for example, which allows for power function singularities. So the function space assumptions are unnecessarily restrictive. And also, we use the method of successive approximations, which involve very long calculations. And successive approximations by itself, this was not rigorous. So we had to verify the solution using Laplace transforms, which was again, or using substituting into the differential equations, which was again a long calculation. So this was, it was valid. The results are correct, but they can be improved by using other methods and by trying to go to bigger function spaces. So let's look now at an algebraic interpretation. So the system of equations 2 to 3, all right, every Caputo derivative can be interpreted using this result of Lutschko-Gorin flow. Caputo derivative can be interpreted algebraically in the field m-1 in terms of this algebraic element S mu and the Taylor polynomial of the function. So here we are, S mu1, S mu2, we have these Taylor polynomials, the right-hand sides are easy, and this we can turn into a matrix equation. So we've got something multiplied by x1, something multiplied by x2, and then moving over to the right-hand side, we have the g1, g2, and these Taylor polynomials, which should be known if we have a well-posed initial value problem. So the right-hand side is a totally known vector. On the left-hand side, we have x1 and x2, which we want to find, and this matrix, which again does not depend on anything unknown. Now, an important point here, these are not real or complex matrices. The elements of this matrix are potentially field elements, not even functions, not numbers, not functions, elements of this abstract algebraic field. So we can do it using linear algebra, but it's not real or complex linear algebra. It's linear algebra over an abstract field. We solve the matrix equation, invert the matrix, multiply, divide, and so on. And this is the expression we get. How can we interpret these? So these are in red, which means they are in the field. They're not yet functional solutions. They're correct, valid algebraic solutions, but they're not functions because we've got this capital S involved. We've got this identity involved. These are not functions. These are only in the field. Luckily, we already have a result from some of Lutschko's papers, which shows us how to interpret this thing. In red is a convolutional quotient as a multivariate Mittag-Leffler function, specifically trivariate. So alpha 1, alpha 2, alpha 3, 3 different inputs into this function. Now, how does this help? Because if you look at the denominator of these two big red fractions, if you multiply on top and bottom by h, mu1 plus mu2, so remember S is the inverse of h, then the first term will become the identity, minus a11h mu1 minus a22h mu2 plus this constant h mu1 plus mu2, which would be exactly in the form like this left-hand side of equation 6, which we can then interpret as a trivariate Mittag-Leffler function, and thence we can solve the system in terms of these functions. So skipping a lot of calculation, let me go to the solution. This is the explicit solution for the general Caputo system. Big, complicated formulae, right? They're actually even more big and complicated than they look because I put ... in here just to fill in. These are the arguments of the trivariate Mittag-Leffler function, because if I actually wrote those every time, then it wouldn't even fit on the slide. Okay, so these are x1 and x2, the solutions. They're complicated, but they are explicit solutions, which means they can be calculated. One tricky thing actually is that the numerics of these trivariate Mittag-Leffler functions are not very well known yet. So this is ongoing work to try to understand better these functions so that these solutions we've constructed will be more useful in actual practical research. So we can consider a few slightly more simple cases. So we have a homogeneous case where G1 and G2, the right-hand sides of the equations, are 0. And then we will have a solution. You see, there is still a convolution in this solution. There's G1 star. So this is ordinary convolution of functions. This doesn't involve any abstract algebraic field stuff. But in a homogeneous case, we don't have any convolutions. This is just a linear combination of these trivariate Mittag-Leffler functions. If the orders are between 0 and 1, then we don't have these finite sums anymore, because n1 and n2 will be just equal to 1, and we will get these relatively nice expressions. Again, ... means these three arguments. And in the most simple cases where you have homogeneous and orders between 0 and 1, and then you get these relatively simple and elegant expressions. And these agree with what we found in previous papers, because remember, the papers that I cited where we studied systems of FDEs, we only did it for orders between 0 and 1. So these results were already known. These results possibly also already known, I think, but these ones are new and these ones are new because when the order can be arbitrary, this was not something that we did in our previous work. So what about the same problem with derivatives of Riemann-Liouville type? So it's easy to set up the two differential equations. It's not so easy to set up the initial conditions. We know we're going to need some fractional initial conditions. Maybe it's not immediately clear what they should be. So let's go ahead with this method and we'll find out at some later stage what initial conditions we should specify at the beginning, because there's only one way really to make a nice, well-posed initial value problem out of this. So here again, we get the algebraic equations. This P is a so-called projector. It's basically what you get from the second fundamental theorem of calculus, fractional integral of a fractional derivative. It involves fractional initial conditions, and specifically, these are the fractional initial conditions that are involved. So Riemann-Liouville derivative to these orders of x1 and x2 at the initial value. This matrix equation can be solved in the same way as before. In fact, the matrix is exactly the same as before. The G1 and G2 are the same. The only thing that's different is instead of Taylor polynomials here, instead of these capital T's, we have capital P's instead. So the calculation is quite similar. This is the explicit solution. So if you compare this with the other equations, obviously I can't fit them all on the same slide, but take it from me that if you compare them, you will see the last terms are the same for Riemann-Liouville and for Caputo. So the G1 star something, G2 star something, they are exactly the same in both cases. Where the solutions differ are these terms, which come from essentially the initial values. So these x1 0k, x2 0k, these are initial values, and those are different between Riemann-Liouville and Caputo. So that's the difference between the solutions we get for these two types of systems. Again, we can consider the homogeneous case. It simplifies a bit. The case of orders between 0 and 1, we don't have any finite sum anymore. And if it's homogeneous and orders between 0 and 1, then we've got this, again, relatively nice and simple solution. Now, an interesting point here is that, remember, orders, that's mu1 and mu2, are between 0 and 1. So we have powers here, t to the power mu1 minus 1, t to the power mu2 minus 1. These are negative powers of t. So that means the solutions are unbounded at t equals 0, and this is necessary. This is the only way to solve the equation, because, of course, we had a well-posed problem. The solution is unique in the function space c minus 1. So that means if we tried to solve it in the space of, for example, absolutely continuous functions or continuously differentiable functions on the closed interval, if we assume boundedness at 0, differentiability at 0, we would not have any solution. It's not solvable in that space. So that's one of the interesting things about fractional differential equations. Sometimes you need to go to a bigger function space to allow for some singularities at the initial value. Otherwise, you will not have any possible solution. So let's recap the advantages of this Mikusinski method. Okay, I've used it to solve some systems, but how does this compare with the way some such systems were solved before? Well, larger function spaces, this is, as I mentioned, important in some cases to allow for singularities. Fractional orders can now be anything, any complex number, with positive real parts. It's a fractional derivative, not just real numbers between 0 and 1. There is less calculation here, or rather, the difficulty is hidden in abstract mathematics instead of in long calculations. So in the previous methods with successive approximations, we did not use any abstract algebra, but we had to do some big integrals and big sums, and there was a lot of work in it. Here, we've hidden the work in this matrix over an abstract field, which is inherently a more mathematically advanced concept, but handling it once you have the abstract maths you need is more simple. We don't need to verify that the solution is a solution because the construction shows that it is a solution, shows that it is unique because we have a field. And again, in the field structure, multiplication, division, and all this stuff works naturally. So let me conclude the talk here. We have Mikusinski's operational calculus. This is an algebraic method for solving differential equations, formally similar to Laplace transforms, but it works in bigger function spaces. Mikusinski applied it to ODEs in the 50s. Luchko and others applied it to fractional ODEs since the 90s. Now it's being applied to more general fractional operators, for the first time to fractional PDEs, and now also to systems of fractional ODEs. So future work, we can use different kinds of operators, maybe not only Riemann, Lieber, and Caputo, but other sorts of fractional calculus. And we want to figure out how to extend from a coupled pair to a coupled system of not only two equations, but n equations, maybe an n by n matrix and so on. It will be more difficult, but I think, again, we could find an explicit solution. I include one slide just for people who are interested in fractional calculus to mention a couple of events in this field. So there is the Isaac Congress in Kazakhstan. Probably many people already aware of this. I think I saw, in fact, some names in this session that are already registered to this session in Kazakhstan. But I'm organizing a session there on fractional calculus and fractional differential equations together with Yuri Luchko and Joel Restrepo. Well, the early bird registration is up to 15th of May, which has passed, but you can still register. You can still send abstracts. My email address is on the last slide of this presentation. This is a very big, very high-level conference, generally on analysis. We also have a conference specifically on fractional calculus, which is also going for many years. It's the main conference on this field specifically, and this year it will be in Algeria in December 2025. The abstracts are not only abstracts, they are in IFAC format, which is basically a short paper. If you want to appear in the proceedings, the paper should be like 6 pages long, double column format, or you can submit something short, just 2 to 4 pages, in order to give a talk without appearing in the proceedings. So according to the website, the first submission deadline is 15th of June, but I suspect that that will be extended. References, here we've got the textbooks, some older papers, Mittag-Leffler, Prabhakar. Here are a lot of papers on Mikusinski's operational calculus in various settings, some more recent ones in generalized fractional calculus, continuing. Most of these I think I have already mentioned on the slides. The last reference here is my paper on the work that I presented today, which has already been submitted and is in revision. So I will stop there. Thank you very much for your attention.